Modern life is totally intertwined with the innovative products of the electronic revolution. But just what are the powerful engines that enable these products to work? We find them hidden in small packages, attached to circuit boards. They are microchips, made on tiny pieces of semiconducting materials, usually silicon. A chip can contain many millions of miniature electronic devices, all wired together to form an integrated circuit. State-of-the-art chips contain billions of components. But what exactly are integrated circuits? And how are they made? Making the microchip at the Limits 3 will answer these questions and reveal a manufacturing process that pushes the limits of technology, just as it will push your imagination. In 1947, not even the scientists who invented the first transistor could have predicted the electronics explosion. In that era, the electron vacuum tube was the dominant electronic component. Tubes are large and fragile, and are prone to early failure from overheating, so that early computers filled entire rooms and required extensive air conditioning systems. A replacement for the vacuum tube was necessary if computer development was to continue. That replacement was born in the laboratories of Bell Labs. In 1947, three scientists, William Shockley, John Bardeen, and Walter Brattain, announced the birth of the transistor. It was an unsophisticated device, formed in a small piece of germanium, but it functioned like a vacuum tube. Because it operated on small amounts of electrical power, it ran cool, was smaller than a tube, was much less prone to breakage, and had a lifetime measured in years. The invention of the transistor quickly sparked an infant industry producing devices based on semiconducting materials. Early solid-state devices, such as transistors, diodes, resistors, and capacitors, were manufactured one to a chip and became known as discrete devices. These in turn supported a growing demand for solid-state computers and consumer products. From discrete devices, it took two breakthroughs to launch the integrated circuit, which is two or more components wired together on a single piece of semiconducting material.
Welcome to CEDA-Labz. So we are starting with our first module, Introduction to Integrated Circuit Technology. There is no doubt that our daily lives are significantly affected by electronic engineering technology. This is true on the domestic scene, in our professional disciplines, in the workplace, and in leisure activities. Our world is full of integrated circuits. You find several of them in computers. For example, most people have probably heard about the microprocessor. The microprocessor is an integrated circuit that processes all information in the computer. It keeps track of what keys are pressed and if the mouse has been moved. It counts numbers and runs programs, games on the operating system. Integrated circuits are also found in almost every modern electrical device such as cars, television sets, CD players, cellular phones, etc. But what is an integrated circuit and what is the history behind it? Digital circuit design has evolved rapidly over the last 25 years. The earliest digital circuits were designed with vacuum tubes and transistors. In 1940s, the stage was set, the initial inventions that made integrated circuits possible. In these years, vacuum tubes were used. Just as the transistor, the vacuum tube can switch electricity on, or off, or amplify a current. The vacuum tube looks and behaves very much like a light bulb. It generates a lot of heat and has a tendency to burn out. Also, compared to the transistor, it is slow, big and bulky. The first digital computer ENIAC, for example, was a huge monster that weighed over 30 tons and consumed 200 kilowatts of electrical power. It had around 18,000 vacuum tubes that constantly burned out, making it very unreliable. When the transistor was invented in 1947, it was considered a revolution. John Bardeen and Walter Brattain and William Shockley succeeded in creating an amplifying circuit utilizing a point-contact, transfer resistance, device that later became known as a transistor. September 12, 1958, Jack Kilby at Texas Instrument had built a simple phase shift oscillator IC with 5 integrated components: resistors, capacitors, distributed capacitors and transistors. This first integrated circuit was tested and it worked properly. Integrated circuits were then invented where logic gates were placed on a single chip. The first integrated circuits that were developed in the early 1960s contained less than 100 transistors on a chip and are called small-scale integrated circuits, SSI. Medium-scale integrated, MSI, circuits, developed in the late 1960s, contain up to several hundreds of transistors on a chip. With the advent of VLSI, large-scale integrated circuits in mid-1970s, designers could put thousands of gates on a single chip. At this point, design processes started getting very complicated, and designers felt the need to automate these processes. Chip designers began to use circuit and logic simulation techniques to verify the functionality of building blocks of the order of about 100 transistors via CEDA tools, but circuits were still tested on the breadboard and the layout was done on paper by hand. As technologies became sophisticated, in early 1980s, designers could design single chips with more than 1 lakh transistors, and these were called VLSI, very large-scale integrated circuits. Because of the complexity of these circuits, it was not possible to verify these circuits on the breadboard and prepare manual layout. And this trend has continued to the present day with 1 million transistors on a chip by the late 1980s. Ultra-large-scale, ULSI, circuits came in 2004, with up to 1 billion transistors on a chip. You must have heard about Moore's Law. Moore's Law is the observation that, over the history of computing hardware, the number of transistors on integrated circuits doubles approximately every 2 years. The law is named after Intel co-founder Gordon E. Moore, who described the trend in his 1965 paper. His prediction has proven to be accurate, in part because the law is now used in the semiconductor industry to guide long-term planning and to set targets for research and development. Now, let's see why this integration was done. What is the need of integrating these ICs up to this extent? What advantages do ICs have over discrete components? First of all, size, which is submicron instead of millimeter or centimeter. Secondly, smaller size of IC components yields higher speed and lower power consumption due to smaller parasitic resistances, capacitance and inductances. And also, switching between 0 and 1 is much faster on chip than between chips. Third factor is of cost. As you can see, because of lower power consumption ripple effect, less heat is produced, which leads to cheaper power supplies, finally leading to reduced system cost. Integrated circuit manufacturing is versatile. Simply by changing the mask, new IC can be designed that is. These are erasable and reprogrammable. However, designing the layout, changing the masks, is usually the most time-consuming task in IC design. As technology became sophisticated, manual layout and breadboard testing was not feasible. It became almost impossible to design and test the functionality of building blocks of the order of about hundreds and thousands transistors. Computer-aided techniques or electronic design automation, EDA, techniques evolved and became critical for verification and design of VLSI digital circuits. CAD, that is, computer-aided design, is the use of computer systems to assist in the creation, modification, analysis, or optimization of a design. CAD software is used to increase the productivity of the designer, improve the quality of design, improve communications through documentation, and to create a database for manufacturing. These logic simulators came into existence to verify the functionality of these circuits before they were fabricated on chip. CAD tools do automatic placement and routing of circuit layouts. Logic simulation assumed an important role in the design process, and designers could iron out functional bugs in the architecture before the chip was designed further. Hence, design time is reduced and there is less human brain utilization. Therefore, chances of human error are reduced. A typical design flow for designing VLSI integrated circuit is shown here. This design flow is typically used by designers who use HDL for designing any IC. As a designer is not able to think all connections in terms of gates, that is why we need design flow. First step is design specification, then is behavioral description, RTL description, next is functional verification, then logic synthesis, gate level netlist, logical verification and testing, floor planning. Next is place and route, then physical layout, further layout verification, and layout implementation, and then finally fabrication. Let's understand each step of design flow in detail in upcoming slides. In any design, specifications are written first. Specifications describe abstractly the functionality, interface, and overall architecture of the digital circuit to be designed. At this point, the designers do not need to think about how they will implement this circuit. Then a behavioral description is created to analyze the design in terms of functionality, performance, compliance to standards. The behavioral description is then manually converted to an RTL description in an HDL. From this point onward, the design process is done with the assistance of EDA tools. Functional verification is done to verify the functionality of code. If it is functional, we proceed further, otherwise we move back to previous step, that is, RTL description, and debug the fault. Next is logic synthesis. Synthesis means conversion of RTL description to a gate-level netlist. Logic synthesis tools convert the RTL description to a gate-level netlist. A gate-level netlist is a description of the circuit in terms of gates and connections between them. Here, in logical verification and testing, synthesis tools ensure that the gate-level netlist meets timing, area, and power specifications. If it doesn't meet these requirements, we need to recheck our RTL description and modify the code and follow the design process from there all over again. Floor planning is planning of design according to the specified design specification. Gate-level netlist is then automatically placed and routed by automatic place and route tool, which creates a layout. The routing and placement phase decides on the placement of cells of the target hardware. Wiring inputs and outputs of these cells through wiring channels and switching areas of the target hardware are determined by the routing and placement phase. The output of this phase is physical layout, and it is specific to the hardware being used. Physical layout is the CMOS level design of gates. This physical layout is then tested and verified. As the integration size of VLSI chips become larger, design verification and testing at each design stage is vitally important, because any errors which sneak in from the previous design stage are more difficult to find and more expensive, since once found, we need to redo the previous design stages. Physical layout is also tested and verified. In case of failure, we go back to floor planning, and in case problem is not solved, we further move back to RTL description. In case of success, layout is implemented and chip is fabricated. Now we will see different process technologies. In VLSI process we have two types of technologies. First one is bipolar technology and second is MOS technology. When we are going for bipolar technology, the basic element is BJT, that is, bipolar function transistors. If we go for MOS technologies, basic element are NMOS, PMOS, CMOS, and BiCMOS. The advantage of BJT devices is that it is faster than MOS devices, but it needs a 5-volt power supply. So it generates more heat and they generate more power dissipation. If we are going for MOS devices, it need only 3.3 voltage, so heat dissipation will be also very less. If we want to get speed and power, then we will go for this one, that is BiCMOS. It is the combination of bipolar and MOS technology. So we can get a high-speed device with low power. Now we come towards chip manufacturing process. In chip manufacturing process, first step is silicon ingot, means making the silicon in its pure form. After that they are sliced into wafers, then the wafers are cut into the dices. We can see similar dices, and then these dices are tested. After testing we will get only few dices, because all the dices are not having the characteristics what we are expecting. After getting the dice we will go for the masking process. This mask is designed with respect to our layout design. So we can get the design in the dice during the masking process, and we will go for other different process and get the dice having our design. We can see now different products and manufacturers. First one is processors, second one is communication, and third one is consumer electronics, and fourth is programmable devices. In case of processors, the major manufacturer are Intel, AMD and Sun Microsystems. In communication domain, Qualcomm, TI and Cisco are the major manufacturers. In consumer electronics you can see Sony, Nvidia, LG, Samsung and lots of companies we can see in this consumer electronics, and then the last one is programmable device. In this one major manufacturers are Xilinx and Altera. Now we will discuss about the scope of VLSI. What are the domains in VLSI, which are the field in which we can work in VLSI, what type of jobs we can get in VLSI domains. There are different domains like processor domain, memory design domain, communication and consumer products design domain, and also intellectual property design, means IP design or cell design, like that lots of domain can be there. If we are going for fields, we can see RTL design, that is resistor transfer level design. Here we are entering our design using HDL, and then testing and verification. This is one of the major parts of the design flow. Here we have to spend more time and more care for the verification. Different types of verification are there, they will test for the functionality and also timing, then the layout design. In layout design they are making layout in the form of GDS tool, which means graphical design system tool. Then programmable logic design, if we are going for FPGA design, there is no need to go for layout. This programmable logic design will do that FPGA and CPLD's designs. Then coming to this EDA tool, which is an electronic design automation tool. These tools help the designs to reduce the complexity of the design and also reduce the time needed for the design. The main manufacturers of EDA tools are Cadence, Synopsys, Mentor Graphics, etc. We can also do the design manually. The thing is, if we are going for EDA tools, it will make our complex design simpler. So we can also reduce time needed for design. Nowadays the integration is going very larger, so it is difficult to go for manual design. Now we will see the challenges and trends in VLSI domain. These three parameters are the main challenging parameters in VLSI. These are called as design constraints, power, frequency or speed and area. Every chip manufacturer want to reduce their power dissipation, want to increase their speed and also want to decrease their area. These three parameters are interrelated either directly or inversely. Let's see how it is related. According to Moore's law, number of transistor per integrated circuit will double every 2 years. Here you can see in this processor graph the number of transistors in a chip is increasing every 2 years. Coming to frequency trends, the frequency is doubling every year or 2 years. So every year the frequency or the speed of system is also increasing. How they can make faster design? They have to reduce the design. Every gate comes with its own delay. So if we are reducing the individual delay of the gates, then the system or the chip become faster. Here, in the graph we can see the power and area is inversely proportional. The area is decreasing and the power is increasing. We can see in the graph of this Intel processor, how the power is increasing if we are going for less area. So the new processor needs heavy heat sink and more fans for cooling their power dissipation. Here we can see the area technology. 90 nanometer means length of the gate of a CMOS transistor. So, In 1993 the gate length is 0.5 micrometer, now it is around 45 nanometer. So the size of the gate is reducing. If the size of the gate is reducing, means we can reduce the size of the chip and the area of the chip. That's why now the chip size has become too small. Currently we are mainly using 35 nanometer to 38 nanometer. 65 nanometer is also used but very rarely. Let's go back into the flashback in order to recall what we have learned so far in this module. We learned about how integrated circuits were evolved from SSI in early 1960s, MSI in late 1960s, LSI in 1970s, VLSI in 1980s to ULSI to the present day. Then we learned why we needed CAP tools. Just because design became complicated and complex with more and more gates on a single chip, due to which manual layout and breadboard testing became impossible. Then we came up with design flow for designing any IC. Can you recall those steps? They were design specification, behavioral description, RTL description, functional verification, logic synthesis, gate level netlist, logical verification and testing, floor planning, automatic place and route, physical layout, layout verification, layout implementation, fabrication. Next we learned about how a chip is manufactured. Can you recall? Pure form of silicon is sliced into wafers, then wafers are cut into dices, then we test these dices. After that verified dices are masked according our layout design. Challenges faced by designers are to meet the design constraints, which are speed, area, power. Speed should be high, less area and less power consumption. Now, can you answer these questions?